Everybody, it's Tyler here at Chezy Champs, checking in team number 1690 Orbit, coming out of Israel. One of my favorite teams in all of FIRST. One an absolutely incredible rollout they've had this year and in years past as well, too. This team has really become a Tier 1 team here, and I can't wait to talk more about it. So in order to talk about this, we have Guy, Leary, Omri, and Noam. And we're going to be diving, of course, through this robot. Incredible autonomous modes, awesome intake. This shooter is incredible. All here coming up on Behind the Bumpers.
Giving you a voice.
Making it loud our own way.
Welcome to the fun.
We'd like to thank Stryker for their continued support of FIRST Updates Now. Stryker's internship portal is now open and available. Discover internships and rotational programs located around the world, including their headquarters in Michigan, when you go to careers.stryker.com and click on Students and Graduates. We'd also like to thank Kettering University. Kettering University is where robotics students come for their education. Over 30% of those who attend Kettering University were in high school robotics, and you can keep going with their BattleBots, VexU, esports, and FIRST mentorship programs. If you are a U.S. student grades 8 through 12, scan the QR code to stay up to date on info and events happening at Kettering and get a free Kettering t-shirt when you sign up by December 12th, 2021.
So starting out here, we're of course going to follow that power cell journey, talking about this intake. Any changes or iterations you might have made too over the last couple of years as well would be great to hear.
Yeah, so actually we have been doing some changes from 2020 of the beginning of the season. We beginning at the season, we beginning with 2 rollers, and then actually we added the 3rd and 4th. We saw at the beginning that the power cell is actually shooting up from the robot, so we added the 4th one that will direction the power cells into the spin axle. Also, you can see that, yeah, all right.
So it's kind of just nice and gentle with it now as it kind of pops it in. Yeah, that makes sense.
So what's special that our intake is very, very flexible.
Yeah.
And also with just 2 screws and 2 rivets, we can just replace it all, take it out, and replace it in just like 5 minutes, which was a really great improvement from the first competition in the Israel district.
Yeah, your team actually might have more experience coming into this event in Infinite Recharge than any other team here.
Yeah.
With all the events going on in Israel as well too, so that's great to see. Just a question on this, like from the simplicity of it. When you initially looked at Infinite Recharge, were you looking at a flexible intake and kind of making it this simple, or talk to me more about that?
So actually we designed it in a way that it's really flexible, and I think at the start it has like 2 plates, and then we just moved to 1, really to get it flexible and really to maintain. That is.
Yeah, well, let's go next into the Spindexer coming up on here. So I want to talk more about just kind of some of the design. I mean, this is just a really cool design layer that you have here. So talk to me a little bit more about that.
Yeah, so as you can see, like from the beginning of the season, we saw that the balls have a lot of friction with each other and with the other materials. So we decided that we wanted to keep them, first of all, separate from each other. So we made the Spindexer, which separates them from each other. And after doing a few prototypes, we saw that the balls can get really stuck inside the Spindexer with the walls. So what we did is we added this really cool thing that it's just 2 circular plates and a tube that spin freely. And anytime the ball touches it, like anywhere you throw the ball, as you can see, it just it doesn't get stuck. Oh, sorry, it doesn't get stuck. And
can we put a couple more power cells in and we see how these kind of come in together?
It don't get stuck, and there's like no friction and any jams inside. And like the whole idea was to stop any jams here. So another thing we did is, as you can see here, you see what happened? So another thing is that we added this is the wheel that takes the balls from the Spindexer into the shooter. So it's just actuated with a piston that pushes it down and takes the balls up. And the cool thing is that we have we connected it with the gears to another wheel, and it spins in the opposite direction. And what happens is that whenever there's a ball on top, it just pushes it away, so there's no jam when it comes into the shooter. And we added another Omni gear here, which just spins freely, and that's too, it just helps us get rid of any jam that can possibly happen in the
Yeah, I mean, we can see it here. The proof is there. At what point did you make these changes?
Okay, so like we had a really long prototype session when we started the season, and we started without the rollers.
Sure.
And like the first idea was just the spindexer, and then we added the rollers when we saw there was a problem. You can see that it's a really simple build. It's just a rivet a rivet down there that holds the tube inside.
Yeah,
Like, it's really
I mean, it's
simple.
great implementation, obviously, right? And it's been working out awesome for your team. Let's keep moving on into your shooter here. The very massive shooter that you have. Love to hear more about it. Looks like obviously adjustable hood. Not turret. You guys have a sword drive, so you don't really need that, right? So talk to me a little bit more about this whole kind of just assembly and kind of how the ball passes through on here as well.
All right. So I'll start with the requirements. At the beginning of the season,
Wow.
we decided that we want first we wanted to shoot from the far of the trench. Also, we wanted to shoot from the close side of the trench over a defender, and also from the triangle close to the power port into the inner circle. Also, we wanted to move quickly underneath the trench. So as a consequences, we designed a shooter that can fold up and down, and really in any angle, any direction, and that will allow us to shoot the balls.
I got to ask this, and this might be a programming question asking here. How are you ensuring that the hood is getting that right position? Because there's so much travel and so much weight on something like that. Tell me a little bit more. How do you make sure that the hood is getting the right spot each time?
So this subsystem has a lot of forces acting on it. So we have the gravitation force, which pulls it down, and we have the acceleration of the swerve. So in each position of the arm, the forces are acting differently. So we make a 2D vector in like the vertical plane, and we project it on this angle perpendicular to the arm, and find the force acting on it in the direction of movement.
Yeah, it makes a lot of sense in there. I do want to ask on your shooter as well, too. You got kind of this extra weight on the flywheel, but you have so much weight going on in the middle here. Was this kind of modified over time on your flywheel, or how did you like determine like this is the configuration and the weight amount that we want to go for that?
So actually, in the first week of the season, we built a very complex prototype, and on it we checked on all the parameters, the gear ratio, the wheels, diameter, and all that stuff. And at the last we started on this design. We added the flywheel actually I think later. It just works really great. I do want to add about the path of the ball, so we can show here just a second.
Sure.
So the balls is really as the feeder is just going down with this piston, and the balls is just getting into the tower. And what is really special here, that the balls are really when they are up, so they are tangential to the center of the rotation of the arm. So this is allow us to get a ball from the feeder at any given time and to shoot it. So it's really unique. Also, we added a disc brake in order to really stable that whole shooter.
Yeah.
We wanted to eliminate the backlash that it's creating from shooting the power cells, and really hard. So this is it.
Yeah, I mean, and for those who haven't seen some of your events, the last couple you've played, the Jerusalem one comes to mind to me. Like, I mean, your shooters have just been so accurate. It's so cool to see. Let's keep moving on. Leroy, I know you're going to talk about the climber here, which I'm really want to hear more about, especially how you chose to put this kind of in the middle of your spindexer.
Okay.
And then we'll go into your sword drive as well.
So first of all, something cool about the climb is that we designed it so it's in the middle of the robot, together with the center of gravity.
Sure.
So what helps us is that when we pull the robot up, so we made the really it doesn't need to be so sturdy, the climb, because it just needs to pull it up. There's no like side force, and that helped us make a really lightweight and like compact climb.
Do you know how much this weighs about?
This weighs about like 1 or 2 kilograms.
Sure, yeah.
Okay, and so that's really cool. And another thing that's really cool about this is that, as you can see, in the base of our climb, we have a 3D printed part, and this is the connection to the robot. Now, you probably think that it's a really bad idea because it would just break, but the cool thing is that this climb is really tall and it can like get hit by anything.
Sure.
And the last thing that we want to happen is for one of these profiles to get bent or anything to happen to them, because that would be a really long build and it would like be really hard to replace it.
Yeah.
So we made this part like easy to replace, and it happened to us in the last competition. It just broke when we got hit when we were trying to climb. So it was a 5-minute fix instead of a 45-minute fix, which was really cool.
One thing I want to ask you is just on the actual climber pieces here, just a little 3D printed piece, just a little bit of lip here. What made you choose just to go with, I mean, that's...
No, this is actually not the hook that we climb with.
Oh, okay, gotcha.
Wait, I'll show you the hook.
Yeah.
It's
I mean, I was just going to say the margin of error in that's got to be crazy.
Yeah, that would be really hard to climb with. This is our hook. It actually starts folded like this. This is all folded inside. It's like this. And then it goes up because of these surgical tubes, and we have a string that takes it up, lets it go, and then this is flung up because it's with surgical tubing as well, and then the string is connected here. So this is the only part that really needs to take the whole weight of the robot. Mm-hmm. That's why we made this, and so this holds the whole robot, and it's really cool. Now, another thing about our climb is that we have 16 motors that we can use, 16 PDP ports. So what we did to make it the maximum usage of these ports is we made a really cool gearbox, which we took from 148 2014 robot.
Sure.
We took the design and changed it for what we needed, and it actually has 3 stages. Now the cool thing is that it has 3 stages. So the first one is moving the belts, the vertical belts for the shooter. So that happens the whole game, and what makes that happen is this is a gearbox that has two gears in the sides, and the motor is connected to a gear that is on a plate with another gear, meshed with another gear, which stands vertical, isn't touching the other 2 gears. And it's held with a pancake piston throughout the game. And when that spins, that's when the vertical belts spin. And then when we want to put the climber up in a really, really speedy fashion, we take out the piston, and then when the motor spins the gear, and the gear that's meshed with it just goes right, for example, and spins the other gear that's on the gearbox, and that's a smaller gear, so it spins faster. And then when we want to go down, we just change the direction of the motor, and it just goes to the other side and goes down with a larger gear, so it's more strong and a little bit slower. And
let's wrap up here. We're going to be talking about your swerve driving, a little bit about programming as well too. So talk to me about anything in particular on your swerve, and I'm really just delighted to talk a little bit more about what's going on in programming your robot too.
Okay, so about our swerve, we made an in-house swerve. We made these parts ourselves. So as you can see, this is one of our wheels, and it has a bevel gear connected together with it. Now this is made of aluminum, and it's coated with anodized with infused carbon, so it's really cool. And this is another bevel gear made out of brass. And the cool thing about these two materials is that they self-lubricate each other, so we don't have to use any grease in our swerve.
That's awesome, yeah.
Yeah, so that's really cool, and it works really well.
Yeah.
And another thing is that we saw that there were 2 extrusions on the ground when we play, so we didn't want to ruin our swerve drive, and we wanted to be able to come at any angle to these. So we made these, which are our swerve defenders, we call them. Protectors.
Especially going over those berms when they were in place.
You can see how they look. The wheel comes from here, from the center, and they protect them from the sides from any angle. And we made many prototypes for this from the beginning of the season with different materials and different angles and shapes, and this is what we came up with. And we made it from Delrin
Yeah.
And you can see how many bumps on it has. And this is from our less functioning robot, so it helps us a lot.
Absolutely. Well, let's wrap up on this robot here. Talk to me about some of the programming. Orbit 1690, you know, your autonomous has just been absolutely just killer, just knocking out the competition that way. You know, you watch so many matches you play and you're already up by, you know, 80 points by the time autonomous ends. So talk to me more about that. And of course, you know, with anything else as it goes into your systems, how that's been working out for you too.
So we actually, we have two main principles when we write our code. We want it to be as generic as possible, and we want to learn from it as much as we can. So we wrote most of the tools we use ourselves, which allows us to better understand what we use, and we learn while we make it. So one of the tools we made is our Pathfinder, which Noam can talk about more than me.
Yeah, so it's right here. So this is our path planning software. It's custom made, and this software allows us to put in some waypoints, which include position, angle, momentum, omega, all these nice things. And this allows us to generate an optimal profile into the robot, and the robot could drive it during autonomous. Some of the mathematical functions that go into defining the curve of the path are Bezier curves, Hermite-Spline, and other neat stuff. We also do some physical calculations to find the optimal trajectory and the velocities for the robot in real time. So, because we have one driver, that's due to one person could be correlated with himself more than two people. So we have one controller, and the driver has to do a lot of stuff. So we use automations to make his life easier. So we have new image processing, and the robot has an algorithm. We call it an algorithm to track our position in each time. We call it the pose tracker. So we use it to do various stuff. The most cool thing we do with it is the auto drive, and we drive automatically during tail up, like autonomous during tail up.
Wow, okay.
And you can see the drive from like the trench to the safe zone near the power part. It's the same every time. If you look at it, you can see that.
So they just like you just press a button and it just does that, or how does that? What's the actual process
what we do
for
is
that?
we combined a lot of data from robot, from swerve, image processing, and our gyro to always know our position. And we use our position, our heading, omega, acceleration, velocity, everything.
Wow.
And according to that, we know our position. And then we do some physical calculation using some kinematic formulas, and to calculate the optimal way to drive to a certain point. So one of the certain point we usually drive to is near the power port. So we just calculate the ideal path to it, and the robot drives it itself.
So I just want to make sure I heard you correct. You said only one person's driving the robot during the match, nobody else. Yeah. I would have never guessed that. That is so awesome to hear the automation that's gone in for that.
Yeah, if you can see, it's like all the teams come with like fancy driver station.
Yeah.
We come like with
just
only
a controller,
laptop, cable, and controller.
Yeah.
That's it. We're very minimalistic. Another
well, at least
cool
on the
thing,
driver's station you're minimalistic. I don't know about the robot being that way.
Yeah. Another cool thing we have is our new custom-made desktop, desktop application dashboard. So now we're disconnected from Unreal, so we don't have the stream. So we made this desktop application from scratch, and this allows us to visualize data really nicely, like the position of the robot in real time on the field. And we can use inputs like keyboard shortcuts and other cool stuff. So that's a new tool we made.
And another thing, as we talked about, is our own image processing using the Raspberry Pi. We have a limelight on the shooter, but also beside, as you can see over here. But besides, we also have the camera over here, which connects to a Raspberry Pi. It has a green over it. We put it down because we can better calculate what we want. We can write our own code, which is more specific to the target. and then we can get a more specific distance to the target relative to the robot.
Well, 1690, your robot absolutely lights out once again. Can't wait to see it compete here. Chezy Champs, for those who haven't seen it, go back and watch some of the off seasons as well too. This team has competed in, because this robot is absolutely amazing. Representing Israel great, but representing first in an awesome way as well too. So thanks for taking time. Good luck here at Chezy Champs, and can't wait to see your team compete in future years. Thanks a lot.
Thank you.
Thanks to Kettering University for their support of this video. Don't just sit in class. Kettering University is the only school in the U.S. that allows you to work as an engineer your first year with their 3-month on, 3-month off co-op programs. If you are a U.S. student grades 8 through 12, scan the QR code to stay up to date on info and events happening at Kettering and get a free Kettering t-shirt when you sign up by December 12th, 2021. We'd like to thank Stryker for their continued support of First Updates Now. Stryker's internship portal is now open and available. Discover internships and rotational programs located around the world, including their headquarters in Michigan, when you go to careers.stryker.com and click on Students and Graduates. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow, and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.